today is going to be another sort of special topic, and it's actually really important. It's actually one of my favorite things because it is so useful. We're going to be talking about using nuclear Overhauser effect in structure and stereochemistry determination, and I'll try to show you why I think this is so useful with some examples and maybe relate things to the exam. So in terms of what the nuclear Overhauser effect is, I've been talking about this in C13 NMR, but not why this is useful. So the nuclear Overhauser effect Noe is a change in the intensity of the resonance of a proton or another nucleus I'll put this in terms of protons, but I'm really talking about any sort of nucleus in response to or upon irradiation of a nearby proton. So what do I mean? So let's say from the point of view of a molecule, I mean that you have two protons, of course it could be a proton and a C13, in a molecule like so, where they're near to each other in space, not necessarily in connectivity, but they're just a few angstroms apart in space. And we're going to do something that specifically irradiates one proton. And obviously what you're doing is not a spatial resolution, but rather a frequency resolution. In other words, each proton appears at a different frequency. And so you're going to hit one of these specifically at this frequency. And what that does here is it responds. Now, when you're irradiating, what you're doing is equalizing the population of alpha and beta states. And when you do that, that in turn alters the equilibrium population of alpha and beta states of other nuclei that are nearby. And the way it does this is it opens new relaxation pathways. And since it is a relaxation process, it doesn't occur instantly. It takes time on the order of the relaxation time. In other words, hundreds of milliseconds typically to build up. And so what you see, well, you've seen this in your carbon NMR. There are two reasons in the carbon NMR that your CH peaks, CH2 peaks are bigger than your quarks. One of these reasons is the nuclear Overhauser effect. Carbon that has hydrogens attached to it is nearby to a hydrogen. So when you irradiate the hydrogens, you actually affect the population of alpha and beta states of the carbon. Another reason is relaxation, that because you're pulsing reasonably fast and quarks usually relax slowly, you end up with lower intensity, but one of the reasons is the nuclear Overhauser effect. Okay, so what does that mean for this hypothetical cartoon of a molecule where you have HA and HB that are near to each other in space? It means that if you have a spectrum that looks like this, where you have HA and HB, if I irradiate HA, now the spectrum changes, and now we don't see HA anymore. And the peak for HB gets a little bit bigger. Now, the effects are pretty small in proton NMR. The theoretical maximum HH-NOE is only 50%. And normally you see values that are a lot smaller than that. You might see typically 10%. So what I've drawn here is a cartoon where HA is or HB is appreciably bigger is actually not really the case. It's just going to be a teeny tiny bit bigger. Now, I said this effect affects carbon, and because of the difference in magnetogyric ratio with proton and carbon, you actually have a bigger effect. So with H1 to C13 NOE, there the theoretical effect is actually 200%. So there you can have a peak get substantially bigger. Now, nuclear Overhauser effects involve relaxation. This in turn involves motion of molecules, so like tumbling motions, which means the NOE is sensitive to the size of the molecule, how fast it tumbles, because that's going to affect different types of relaxation molecules. So high molecular weight molecules, so we're talking typically, let's say, greater than 2,000, and these numbers aren't carved in stone, but let's say greater than 2,000, or if you slow down the tumbling by a viscous solvent, then your NOE is actually negative. And the theoretical maximum is negative 100%. For an HH-NOE. And this is important, say, in protein structure determination rather than in small molecule chemistry, which is where we focus. Now these days, if you look at some of the natural products that are getting published in, say, Journal of Organic Chemistry or Journal of Natural Products or in JACS, some of these are pretty hairy molecules. In other words, they are small molecules, but they are big small molecules. And that big small molecule regime is actually a pain in the neck. Because what happens as you go from small molecules that have a positive NOE to big molecules that have a negative NOE is what? No NOE. So medium-sized molecules often end up having 0 NOE. And I really, really don't want to be putting hard numbers on this because it depends on which solvent you're using, it depends on the field strength of the spectrometer, it depends on the shape of the molecule, it depends on the temperature. But I'm going to step out on a limb here and say molecular weight range of, say, 1,000 to 1,500, which is a big small molecule, is often 0 NOE. Or close to 0. And there's a related technique that's called a rotating Overhauser effect that's often used to bring out these All right, I want to show you an example of a traditional Noe experiment, and I'll show you an old example, and then I'll show you an example that's sort of relevant to organic chemistry research. So I just want to show you the general gist of it. It's the first page of your handout. All right, so this is an example from a book by Jerome, which is a nice book. It's actually the precursor to Claridge, the Claridge book that I've given you some readings from. That was sort of a second edition because Jerome had passed away. So here's a molecule. The particular molecule isn't important, but you'll see the issues. So this is an H1 Nmr spectrum of the molecule. And this is an Noe spectrum in which, or this is an Nmr spectrum in which we've irradiated one of the protons. And specifically, we've irradiated this proton. And in doing this, the authors didn't quite equalize the population of it. So you still see a little bit of the peak. The peak has gone from this over to the smaller version. And it's hard to tell whether anything's gotten bigger. It looks like that one has gotten bigger. But the way in which one historically does this, because the spectrum involves such small changes, the way one historically does this is called a difference Noe spectrum. In a difference Noe spectrum, one is literally subtracting one spectrum from the other spectrum. You are subtracting the unirradiated spectrum from the irradiated spectrum, so I'll put a minus sign, or actually I guess you're technically subtracting the FIDs and then going ahead and Fourier transforming. And so I want to point out the features that we see. So the first thing, of course, we see is now the irradiated peak is negative. After all, if we have something where we've almost equalized the population of alpha and beta states, and we take away something where we have a positive peak, you get a negative peak. But I want to show you the features. Okay, the thing that's glaring you in the face in this literally textbook example is that we see a nice Noe. We see a nice Noe over to the peak here. So there's some spatial proximity between this proton and this proton in the molecule. I want to show you some of the other features in the spectrum. Now, one of the things about the traditional Noe experiment is the conditions of doing the irradiation create little perturbations in the spectrum. And actually, to do it right, what you do is you do one spectrum where you irradiate here, in this case about 1.15 ppm. And this one, in order to minimize the subtraction artifacts, you actually go ahead and irradiate somewhere else off where nothing is, like over here or over here. But even with that, there are small perturbations. So this is what you would call a subtraction artifact. In other words, it's not an Noe. We don't have a particular peak up or down. What's happened is there's been an infinitesimally, a teeny tiny shift in the position of this peak because of the irradiation, which gives a positive character on one side and a negative character on the other side. If I were looking at this, I'd know just from recognition that there's no Noe, but another way, a very good way, and something you really should do, is slap an integral on it. And if you slapped an integral on it, of course the integral would go up as area registered and then go back down. And you'd end up, this would be an integral here, so you'd end up with no net rise, no net area. Now, one of the challenges in a conventional and any sort of one-dimensional NOE experiment is selectively hitting this peak here. Because you're trying to hit all of the lines of this peak without hitting this peak. And when peaks are maybe 1/10 of a ppm apart, it's hard to do that. It's easier if you have singlets. I usually tend to go for singlets if I can. Harder if you have multiplets, because you have to apply a band of radiation that's wide enough to hit this without hitting this. And as you can see, we've got an incomplete selectivity here. And so, putting this in another way, if I was testing a hypothesis that this proton is spatially close to this one, and I hit this one, and I see this one get bigger, but I also hit this one a teeny tiny bit, there's this worry in the back of my mind, oh, maybe my hypothesis wasn't being tested completely, because maybe I'm hitting this one as well, and maybe it's this one enhancing this one. So what sort of experiment could you do to corroborate this result? What sort of NOE experiment could you do to corroborate the result from this experiment?
Could you try to hit the number 1 peak?
Beautiful, exactly. And so we would try a corroboratory experiment as well. And where you irradiate here. And usually NOE experiments end up being done in sets. So you're going to do some 1D NOE experiments on strychnine. And this was the part of the course that everyone hated, so I've cut it down. I had you go ahead and hit every peak that could be hit selectively in strychnine. And honestly, it doesn't take that long. Imagine if this were your thesis molecule. It would be no big deal to spend 3 or 4 hours on the Nmr spectrometer for an important problem. But we're 22 people here. You've got other things to do. So I've cut it down to 1 or 2 nice 1D experiments where I basically had pre-selected the key experiment. You will also do a nosy experiment. But the 1D NOE is a beautiful experiment because you can probe very specific questions. So this is kind of a textbook example. I want to talk, I'll give you a real example in just a second and show you something that I think is cool. If I can find my eraser that I seem to have misplaced here. That way I have the emergency backup eraser. Anyway, before I give you a real example and we then look at some nosy spectra, I just want to show you one other point of this, and it actually ties in sort of to thinking about problems that you might encounter. So I just want to point out one sort of thing here, and that's a three-spin system. So sometimes observing an NOE doesn't necessarily mean proximity, and I'll show you an example. So a three-spin system with coupling. And again, I'll give you my little screwy cartoon for things. So imagine that HC is J-coupled to HB, but it's not spatially close to HA, whereas HA and HB are close to each other. What can happen is if I irradiate HA, of course we'll see an NOE to HB, in this case a positive NOE. And remember, this is occurring because by leveling, equalizing the populations of alpha and beta states of HA, I'm setting up new relaxation pathways that are perturbing the populations of alpha and beta states of HB, but that perturbation then ends up altering the populations of HC. And in this particular alignment, we end up with an NOE over here, a negative NOE. So it's usually going to be smaller, so you usually can tell. But let me give you a real example, and I think this was taken from the Jerome book. So the molecule in this particular case was a trichlorotoluene derivative, like so. And in this particular real experiment, so we have an orthoproton and we have a metaproton. In this particular experiment, they irradiated the chloromethyl group over here and observed a 19.2% NOE over here to the orthoproton and a negative 2.6% NOE over here to the metaproton. Now, I guess looking at this particular molecule, it reminds me of your exam problem, and it reminds me, so on your first part of the midterm exam, remember the nitrotoluene problem? And you were there just by using a combination of understanding coupling patterns and the inductive effect of a nitro group, the electron withdrawing effect, the resonance effect of a nitro group, and the effect of a methoxy group. Most of you were able to assign your resonances and figure out among the 2,4 disubstituted isomers and the 2,5 disubstituted isomers. Here, of course, with chlorine, the effects aren't as pronounced. So just imagine in your mind's eye that you had a molecule and you were trying to tell whether it was the 2,4 or the 2,5 compound. And of course, maybe in this particular case, you wouldn't have as clear a differentiation in chemical shift. But if you look at this here, you can imagine if we irradiated, in this case, you would see an enhancement of this orthoproton here, which would be a doublet with only metacoupling, a tight doublet. If you irradiated over here in this molecule, you would see this orthoproton enhanced, which would be a doublet with orthocoupling. So in other words, even if the spectra of these two molecules, the 2,4 and the 2,5 isomer, were very similar in chemical shift, you'd be able to tell from an NOE experiment which isomer you had by telling whether it was a doublet of 8 Hertz being enhanced or a doublet of 3 Hertz being enhanced. So that's an example immediately that I can hand you of the utility of an NOE experiment. Now, the other example I can give you, and again I'll harken back to the exam to a problem that I guess about 2/3 of you did, was the beta-lactone problem. And there we weren't trying to tell stereoisomers apart. But imagine for a moment, I'll again take the beta-lactone case as an example. Imagine for a moment that we had a beta-lactone, and imagine instead of just having a methyl group at this position, imagine that we had a methyl group and an ethyl group at these two positions. And now we had a methyl group over here of unknown stereochemistry. You could now imagine that you irradiate this methyl group, that's going to be your methyl doublet, say, and you ask, is it enhancing the CH2 of the ethyl group, or is it enhancing the CH3 singlet of the methyl group? And you could then address the question of whether your diastereomer was the cis or the trans relationship between the two methyl groups. In other words, whether we had this diastereomer or this diastereomer.
And it would enhance the one that's on the same side of the right?
More, it would enhance it more. And you're asking a very, very good question. So the question that you're asking is basically, is the NOE a litmus test? And the answer is no, and this is why comparison is so important. Now, I didn't happen to include these in the handout for the class, but I have a very similar example, and I'm going to show you exactly what it means, and then we're going to talk about some distances. And actually, you know, I've been kind of harping on the value of molecular models. Molecular models become really, really, really useful when you want to ask questions about distances. All right, so let's take a look at a real example. This is just one I pulled from my own experience. Use of NOEs to determine stereochemistry. And the example I'm going to pull is kind of a cool reaction. It's a name reaction that probably nobody in this room has heard of. It's the Mccoy reaction. And yet, if Professor Van Branken asked you for a mechanism of it, I bet you would all get it. So the compound, the substrate for the reaction is a alpha halocarbonyl compound. This happened to be a silyl ketone, or what's called an acyl silane, and it's a TBDMS one, but you could also do this with an ester. And when you take this compound, alpha halocarbonyl compound, and you treat it with LDA, and then you treat it with an alpha beta unsaturated carbonyl compound, in this case I used coumarin, you get a cyclopropane product, and I'll draw that product for you. Now, the great thing about reactions invented early on in the century is that in the previous century is that every new reaction you invent can get you a name, a name reaction. So this is the Mccoy reaction. All right. So the product that we get is a cyclopropane and of undetermined stereochemistry. And fortunately, in this particular example, we have a 3-to-1 mixture of diastereomers. All right, let me pull down the screen and give us a chance to take a look at the spectrum of these two diastereomers. All right. So we have these two diastereomers, and now we'll call them isomer B and isomer A. And just to get our bearings straight, the region around 7 parts per million is the aromatic region in each of these. The region at over here is our methyl groups on our silicon. Here's our tert-butyl on the silicon. Here's our isolated methyl group, and these are the ring protons on the cyclopropane ring. And so isomer B, we see a similar thing. We see our aromatic resonances. We see our ring CHs. We see our methyl. our tert butyl. And now we see our 2 methyls on silicon. All right. Why do we get 2 peaks for 2 methyls on silicon? What? David? Diastereotopic what? Topic. They are diastereotopic. And remember I said when you have any sort of stereocenter in a molecule, and now you have a methylene group with 2 hydrogens on it, or a carbon with 2 methyls on it, those are diastereotopic. They're topologically different from each other. In one case, they show up at pretty similar chemical shapes. Another case, which is interesting, they have a high degree of what we call magnetic anisotropy. In other words, difference in chemical shape. Now, this is an example where the NOE just shines as an experiment because we have a testable hypothesis built into the molecule. In the diastereomer on the left, the methyl group is going to be relatively close to those hydrogens on the ring. In the diastereomer on the right, the methyl group is relatively far away, and we're fortunate enough to have both of them. So, let's start with our NOE experiment on isomer B. So in this particular NOE experiment, we irradiate that methyl group, and this is the difference NOE, so this is the spectrum of isomer B, and this is the difference NOE. And we don't see a heck of a lot. You can see this is an example of a subtraction artifact here, but you look and you see very, very clearly those 2 ring protons have nice NOEs. If I want to know how big an NOE, I can slap my ruler on this integral. I've already done this. This distance here was 74 millimeters, and that's for 3 hydrogens. And over here, I slap my ruler on this integral, and it comes out to 2.1 millimeters for 1 hydrogen. And over here, I slap my ruler on it, it's 2.5 millimeters per 1 hydrogen. And so if I take 2.1 divided by 74 divided by 3, I find out that that's equal to 0.085, or I have an 8.5% NOE. And if I do the same over here, I find that now I have about a 10% NOE. And so I'm very happy. I irradiate. Get about an 8 to 10% NOE, and I say, great. We know what diastereomer A, diastereomer B is. Now, you want to be careful. So you do this same experiment, and I was fortunate. We have both diastereomers. You do the same experiment here. So this is diastereomer A. We irradiate, and you see a teeny tiny enhancement. It's little, little baby NOE. Over here and over here, it's about 0.5 millimeters each. And this one on this particular example was about 73 millimeters. For 3 hydrogen. So that ends up to about 2% NOE. And it's nice, with both diastereomers in hand. That's great, we've done a comparison. Hey, you irradiate one diastereomer's methyl group, you get a nice NOE, the other you get a little NOE. The first one is cis, B is cis, A is trans. But imagine for a moment that I had gotten this reaction, the diastereoselective, and I had only gotten one diastereomer. And imagine I really, really wanted it in order to make a natural product to be the cis diastereomer, and I do it and I say, oh yeah, look, I got an NOE. Imagine the trouble I'd be in. Because then I'd go through and go on with this and think, oh, I have what I want. And later on, I make my natural product, if I were making a natural product, and I find it doesn't match the published spectrum, and my thesis would be titled Total Synthesis of Epi, whatever the natural product is, or ISO natural product. You know, I'd still get a Ph.D., but I probably wouldn't get a paper in JAX or something with that. So you really need to be careful. This was a good example. Now, if we look in here, there's some teeny tiny hints. So imagine this was the only one I had. There are some teeny tiny hints that this really is the trans one. And if you look at the integrals, I like to slap an integral on everything. Why do I like to slap an integral on everything? Because it's easy to see. If you have a big peak, if you have a doublet that's standing up there nice and tall, it's easy to see it get bigger. But imagine you have a little peak that's split into a big multiplet that's short, and it gets just a little bigger. You may not see it. So you slap an NOE on the everywhere, and you say, oh, wait a second, okay, I've got some subtraction artifacts here, but I see a teeny tiny NOE here. You can see this guy here has just gotten a teeny tiny bit bigger. I wouldn't stake my dissertation on it, but if I measure that integral, it's about 1 millimeter. That translates to about a 4% NOE, right? Because it's 1.0 divided by 73 divided by 3 is equal to 0.04, 4%. And so I look at that and I say, oh, wait a second. So, in other words, if I only had this diastereomer, I wouldn't want to assign it on the basis of that NOE, because we're seeing a little NOE between the cis-phenyl group and the methyl group, and a little NOE with those trans hydrogens and the methyl group, but I'd at least be able to look at this spectrum and say, whoa, pull myself back, even though I wanted the isomer in which the methyl group was cis to the hydrogens, there was enough data saying it isn't. In fact, there's a good deal of data saying it's trans to those hydrogens. So anyway, be careful with NOEs. Usually we're talking about having multiple data sets, multiple NOEs pointing in a particular direction. Now, this brings up, this cis-trans business really brings up a very, very important question. And that important question is, what is close and what is not close? How close is close? All right. Let's talk a little bit about molecular geometry first. Talk about some distances. The van der Waals radius of hydrogen, anyone know it off the top of your head? Few good numbers to keep in your head. What? How long? Okay, let's take a carbon-carbon bond. What's a carbon-carbon single bond? picometers, or I'm kind of an angstrom guy. 1.54 angstroms. So the van der Waals radius is on that same scale. It's 1.1 angstroms. A CC bond, CC sp3 single bond, is 1.54 angstroms. Okay, so that's at least kind of calibrating us. So what does that mean? Okay, that means if 1.1 angstroms is the radius, 2.2 angstroms for 2 hydrogens is going to be touching so 2.2 angstroms is close. So that's at least the calibration. All right. Now the other thing that's important is how NOEs vary. NOEs scale as distance to the inverse 6. All right. I always calibrate myself in my mind by setting up a little table. So when we were talking last time about dynamic effects in NMR, and I said, all right, what's 10 kilocalories per mole? Well, 10 kilocalories per mole becomes slow at negative 50 degrees C. 15 kind of at room temperature is right about the crossover. 20 or a hair less than 20 is sort of crossing over at 100. And we can do similar things here. So let me calibrate myself. So let's take 2.5 angstroms. 2.5 angstroms, if I take 1 over 2.5 to the 6th, that's equal to 4.1 times 10 to the negative 3. So let's say 2.5 angstroms, we'll call that close. And if we say the relative NOE for that, let's call that 1. And then I'm just going to calibrate myself from there. So let me take 3.0 angstroms for comparison. And if I now take 1 over 3.0 to the 6th, I get 1.4 times 10 to the negative 3. And so the relative value is 0.33. And if I do the same for 3.5 angstroms, take 1 over 3.5 to the 6th, that gives me 5.4 times 10 to the negative 4. The relative value is 0.13. Okay, what does that mean? That means if you imagine 2.5 angstroms and say that's close, that gives you an NOE of a certain intensity. Let's say that intensity was 10%, like we saw in our cyclopropane. Now imagine that we have a distance of 3 or 3.5 angstroms. Well, I'd expect to still see some NOE, but that NOE would be weaker. It would be like 3.3% or 1.3%. This is exactly what we were seeing in the cyclopropane case, right? The cis isomer gave us an NOE that was about 10%. The trans isomer gave us an NOE that was sort of, 2%, somewhere around there. It was detectable, but obviously not as strong. Let's call this medium. Let's just continue our calibration. 4.4 angstroms, 1 over 4 to the 6th is equal to 2.4 times 10 to the negative 4. And now we're at 0.06. Now you might say, well, by the time you're at 4 angstroms, that's, let's call it not so close. What do I mean? What do I mean? Well, I mean, you might still get a teeny tiny NOE at 4 angstroms, but it's not going to be a really big NOE. But again, I wouldn't stake a stereochemical determination on seeing that if I see an NOE between 2 protons, and I say, oh, they can't be cis, they can't be close, because I see an NOE, it's very small. You might say, wait a second, he just said in class that you could still see something at 3.5 or 4 angstroms. Now I'm going to calibrate us with models in a second, which is one of the reasons, as I said earlier, I've been making such a big deal about models. I'll give you one other number, 1.8 angstroms. 1.8 angstroms is the distance between two hydrogens on a methylene group. Those two hydrogens are jammed in each other at closer than van der Waals radius. If I take that, the relative is 7.2. So what does that mean? That means if I have two diastereotopic hydrogens in a methylene, and I irradiate one, you may well see a very, very, very strong NOE to the other. That's like the beta-lactone, where you had the two diastereotopic hydrogens. If I irradiated one, I could well see the strong NOE to the other. Okay, what's close? What's far? I made up these models. I didn't have Pymol at the time. I don't even think it had been invented, but it's the same basic thing. It's some molecular mechanics calculations. Okay, so I just took a few systems that I use to calibrate my own thinking. We just saw an example of a cyclopropane with a methyl group on it. And guess what? The hydrogen on the cyclopropane is pretty darn close to a hydrogen. The methyl group on the cyclopropane is pretty darn close to a cis hydrogen. It's 2.4 angstrom, 2.2 angstroms in this particular model. But at the same time, we see 3.5 angstroms to the trans hydrogen, which is exactly the sort of thing we saw in our NOE experiment. Alkenes, alkene stereochemistry. This is great. You have a methyl group on an alkene, and you want to know which hydrogen is cis to it, which is trans. The cis hydrogen's 2.3 angstroms, clearly close, but the trans isn't infinitely far away. It's 3.7 angstroms. I did the same with a cyclobutane. Cyclopentanes can be very tricky. You know, NOEs really aren't a litmus test with cyclopentanes. I put a methyl group on a cyclopentane, and you look at the methyl group, and yeah, it's close to the cis hydrogen. It's also close to the trans hydrogen. You're going to be getting some 5-membered ring compounds, and you're going to have to look at multiple NOEs to see which is close, which is far. I will also point out, and you can't see it on this model, but it'll come up later. When you have a cyclopentane and you have two hydrogens in a 1 and 3 position, if you see an NOE between them, that really only can be cis. You won't be guaranteed to see it. It'll depend on the pucker of the ring, but you will see it if it's cis. All right, or if it is cis, if you see it, they pretty much must be cis. I put an axial methyl on a cyclohexane, and you can see that axial methyl bangs in to the hydrogens here very nicely. This is a methoxybenzene, and you can see the ortho relationship is also good. All right, I want to finish up with a couple of additional comments and one last example. So the experiment that's now run is a PFG NOE, also called a GNOE. So this is a more modern version of a difference NOE experiment. It's an NOE experiment that uses pulse field gradients. And I can talk more about that later, but right now I'll just say it's cleaner than a difference NOE. You'll be doing this with your strychnine sample. Another experiment is a NOSI. We'll be talking more about it later, but it's a 2D NOE experiment. You'll be using it later on. I'll give you one example. Very data rich. And there are NOEs, and again, we'll be talking more about this later on. A ROSI experiment, which is NOEs in the rotating frame. particularly good for intermediate size molecules. Which give near zero NOEs. All right, I want to conclude with one last example. And I'll just show you an example of how beautiful a set of NOEs can be from a Noe experiment where you get multiple data that give you confirmation in stereochemistry. And so this is a molecule, it's a natural product, it's a terpene natural product called ephanamol. And this is a Noe experiment of it. Noe experiments are 2D that give cross peaks based on spatial proximity, so they're NOE cross peaks. And if you look at this, of course, what's cool is we have this 5-membered ring fused to a 7-membered ring. I'll draw it out flat just so you can see it. And of course you have, so we have an alkene here. And of course you have some stereochemical issues because you have a ring junction in the molecule. And I'll tell you now the ring junction is cis. But of course you'll want to be able to tell that because you wouldn't necessarily know that. And there's an isopropyl group, and the isopropyl group is cis to the hydrogens of the ring junction. And so now let's take a look at what NOEs we see and how they help show the stereochemistry. So for example, we see a nice NOE between the hydrogen at 4 and the hydrogen at 11. They're cis to each other, they give rise to a strong NOE. Now you get many more corroboratory NOEs. So the hydrogen at the 3 position, for example, is cis to the alkene group, and they have an NOE, and we see that NOE over here. So you're starting to get pieces of the molecule sewn together on not only the stereochemistry, but also the conformation of the molecule, the shape of the molecule. Remember I told you I have a very simple-minded view about medium-sized rings. I say always start with a cyclohexane and go ahead. You can sort of think of a cyclohexane and then perturb it. And I mentioned later on you're going to get some 7-membered rings, and you can think of it kind of like an extended cyclohexane. We see this here in the 7-membered ring. The 7-membered ring puckers, and so the hydrogen at the 11 position and one of the hydrogens at the 8 position are basically like diaxial hydrogens to each other. And we see that very nice NOE over here. Remember how I said you can see NOEs on alkenes, and we see this NOE here between proton 5 and 15 on the alkene. So this is really a beautiful data set because it gives us information on the conformation and stereochemistry of the molecule. And you could then imagine building a model, looking at your distances, saying it doesn't make sense, looking at your dihedral angles and saying, okay, are we seeing coupling behavior here and coupling constants that match this? Is everything consistent with this model? Could there be any other stereochemistry which could be consistent with the data? Could there be any other conformation that could be consistent with the data? And that's one of the reasons why modeling and NMR work so well together. All right, that's what I'd like to say for today. We'll talk about, I think, the HMBC experiment next time and begin to bring that into our program.